Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to NPTEL Groundwater Hydrology and Management course. We are at now week 1, lecture 4. So this week is about an introduction to groundwater hydrology and groundwater occurrence. So it is very important to touch the basics before we jump into specifics of the course. So please understand that it is more like a sensitization week where we understand different concepts. And some of the very important concepts for groundwater hydrology, movement, recharge, discharge will be discussed in the future. Please look at the syllabus, and this week will be introduction. So let's start with theory of groundwater flow. Soils, rocks, and sediments in the subsurface consist of a matrix of solid minerals, grains, and pore spaces. So when we look at groundwater movement, I have a figure in a couple of slides. It is not only on the deep part of your earth, which is like from the ground. It's not only the deepest part or in the shallow part or in the upper surface. Groundwater can occur anywhere depending on is it saturated, is it moving or not. So soils, rocks, and sediments all in the subsurface consist of a matrix of solid materials. The solid mineral is what makes the rock or what makes the soil. For example, if you say silt, clay, etc., that is particles of the soil. When we say metamorphic magmatic rocks, okay, so those are the rock, basaltic rocks. Those are the rocks that make the material, the soil profile. So the solid mineral grains is very important. However, they are not jammed together. They are not stuck together inside because of their irregularities in the shape. Okay, so they're not like a brick where you keep and cement in between. It will have spaces. Those spaces are called pore spaces. So this space you could see as gray color in the figure is pore spaces and porous or soil media. So the pore spaces have space inside the soil profile where there's no solid material or solid mineral grain, but it is a void space where air and water can get in. We would look into the specifics of what is the percentage, how do you calculate this, etc. But to introduce groundwater, this is where the groundwater would emerge in or introduce itself in, recharge, and stay. It can stay for long in one pocket, or it could connect through the pores, like one pore can be connected to the other pore, and the groundwater can flow. So this is the basic theory of groundwater, wherein water is infiltrating as per the hydrological cycle, and there should be a space inside the solid medium to host the water. Okay, so this matrix always have porous medium. Porous means with spaces. Take your sponge that you use to wash your car or wash your dishes. Okay, the yellow color sponge, most probably you would know, it has holes in it. So the solid material is like a soil. Okay, the yellow color could be like a soil, but it has holes in it. And those holes, depending on where you keep the sponge, can have water or air. If you squeeze it and hold it upside down for a long time, all the water will come out and it's only air inside. Okay, if there's no air, it will be like in a smaller size, squished. But it is not squished, right? So it bounces back because air wants to get in. If you push the sponge in water, what happens? All the pores, all the holes will now be filled with water. The same thing here. If you have rainfall and the soil is allowing your water to get into and store in the porous, that constitutes your groundwater. Starting point for characterizing fluid flow through porous media is Darcy's law. So there is a law called Darcy's law, which is the base and very widely used equation to characterize the flow across the medium, across the porous medium. And that constitutes groundwater flow, because the equation gives you a Q, a discharge as volume, or Q as a velocity. So you can either take the amount of water that flows as groundwater flow through Darcy's law, or the velocity at which it can flow through Darcy's law. So we have multiple media here, or like a sample, let's say A, B, C, D, E, F. So what you could see here is the solid particles, which are in darker color, are arranged in a sorted manner, and it has space in it. And that space can take water or air. And this is the basic theory for groundwater. If the water can get into these pores and replace the air, then groundwater can be stored. It need not fully replace it. We call that unsaturated. But if it is fully saturated, then it can connect to between pores. Look at the other example. The solid material also can have holes, as in you can see some rocks. On the surface, it might have some holes. And some holes can even go through the rock material. And inside that, water can go. Okay. So that is given in your diagram C. In your B, what you see is between the voids, between the space where there is porous space, you can have smaller minerals present in it. So along with water, there will be smaller minerals. And then here, the smaller minerals plus a porous media or porous rock, you can see here. Whereas E and F are more fractures. So it's like a rock with a fracture in it, and water can seep in through it. It is interesting to understand the fracture can store water, but the movement or application of water can also lead to fractures. Because a rock weathers, right? You have to weather the rock to form soil. So while it's weathering, some water particles can get in, and water expands when it is cooled. And so it can actually form cracks in your rock. And those cracks are called fractures. And it can either be small or irregular or more regular pattern, okay, depending on the material of the rock, the type of rock. And they can be connected or not connected depending on the rock material. So once if they're connected, then the water will flow. So from these diagrams, what you understand is groundwater flow, let's say from left to right, can occur, and it's not a river. In a river, you don't have rocks and stones everywhere. You have it on the bed of the river, on the sides, and maybe one or two obstacles inside the river. But here, always the material is present. Always there, like for example, these are the rock materials, then water flows through them. And that is how groundwater flow and aquifer, groundwater table, everything is estimated. Because some people assume that when you talk about groundwater, you have a river flowing underneath your ground. No. Because when you dig a well, what do you see? You see only water. There's no solid particles, only the solid particles on the ground. So that doesn't mean that your water is like a river under the ground. Okay, because you have a well, you dug out the solid, you can see it. If you put back the solid, then the water would relocate and it will pass through the cracks and then flow. So it will still flow, but it will pass through the cracks and flow. Let's take another focused groundwater hydrology diagram for our explanation. So you have precipitation, which is the key resource for water to come in. As I said, it is a function of the fluid, which is here the water. It comes in and hits your surface, and then infiltration happens. So that is a process by which rainfall, precipitation can get into your land. And under the land surface or lithography, what you see is water moves through the soil and is being taken up by the plants, animals, whatever is living under the soil. Okay. And some of the water which is remaining, which is not taken up by the plants, get to go further down. Why does it move down? It is because of gravity. Gravity acts for pulling down for the first initial velocity and also the acceleration of water moving down. So once it moves down, it comes to a level where there is full water across the profile, along with the sediments, along with the solid. So which means at this level, below this level, all the pore spaces is full of water. There's no air. So then you have an imaginary water table line, a line below which you have water in all the spaces inside the solid sphere. Okay, so all the soil you have full of water, soil or rock material, whatever the media is, you have full of water, and you can draw an imaginary line, which is called the water table. Please do not confuse this and this line. This line is your stream flow. So if you stand in a river, you draw a line where the river height is. So from the river height until the ground, it is water, but you don't see any sediments, any solid particles. Here, solid particles are included. So if someone wants to calculate the volume of water, you cannot just take this area and say, okay, now I know the height, I know the breadth, I can take the volume of the water. No, because you have to subtract the volume of the solid. So all these calculations we'll be doing in this class through understanding the equations of groundwater hydrology. So percolation happens and then water comes in and relocates. Some of the water still stays behind as soil moisture, which is the beauty and also the driving factor for plants to survive, trees to survive. Suppose soil doesn't hold on to water as soil moisture. What happens? All the water will fall down into the groundwater. And so there won't be any plant life because plants cannot extend the root that deep. It is very hard for plants to get to that deep because both biomass has to go down and also the pressure to take it up to the top of your plant or tree is pretty high. So the energy consumption is more. You only see those kind of plants in deserts where they have very deep roots or very lateral roots because there's less rainfall. The normal plants, your crops, your fruits, orchards don't do that. Okay, so yeah, you can imagine like a pot plant. If you have a pot plant, the root zone is only little. But if you have a plant where it needs more water, okay, then the root zone will go down. Okay, so this is the way water can occur. Groundwater can occur into your groundwater profile. And once it hits your water table, the imaginary line is created underneath which water can flow. So groundwater flows through that region. So water movement in soils is also very interesting and important to understand. So in this course, what you'll see is we'll define porosity. We'll define this pore space and how it's calculated. Then we will identify how water comes into these pore spaces and how it becomes saturated, field capacity, and wilting point. So just to give a brief, saturation is when all the solid particles are present along with water, which means the void space does not have any air. It's full of water and gravity is still acting on it. That's why water is falling down. So it's falling and splashing. Field capacity is that stage. After you stop watering your soil. What happens is the water moves down due to gravity. So gravity is pulling the water and it stopped because after some time it cannot. The soil holds on to the water. That holding on to water is an intrinsic property of the soil type. And that is where we have some soils as good soils for agriculture, some as very bad for agriculture. You don't expect plants to grow in sand. You don't expect plants to grow in gravel, right? Because water, if you pour, it just goes down. You need a soil that supports plant life by holding on to the roots, holding on to the water, and slowly feeding the water into the plant. So this soil is ready. It's at field capacity, which means all the spaces are full of water or some air. You have some air particles compared to this. But more importantly, the water stops going down and is all available for the plants to take up. There's some very little water which the soil will never give up. Okay, so but it can be kept. It's not a big fraction of the volume of the water. So some water will always be kept, And that you could see in this stage. So now we're moving from here to here, where the plants have taken up the water, or the water has been evaporated from the soil, and the soil is now at wilting point. The soil moisture is now at wilting point, which means any plant growing on that will wilt. It will droop, and if you do not irrigate, it will be replaced. It cannot survive. Okay. So this is a warning for the farmers to irrigate the field. Once you see the plants drooping or the leaf turning yellow in color, which means the plant is suffocating, it doesn't have nutrients. Nutrients go through water, so it doesn't have water. So suddenly he or she can go and irrigate. So this is that stage when all the porous space is almost gone. The porous space with water is almost gone, and the remaining water is held by the solid particles, and it is not given for plants. So think about in the groundwater term now. Now we've discussed the plants. Please go back to the previous slide where we discussed that after plant take up, whatever water is available, it goes down to percolation. So here, these two stages would have some water coming down, where field capacity is almost done, but still some 1 or 2 droplets is there, which can contribute to your groundwater. But in saturation, water still moves down. Okay. So can you expect groundwater flow in a good groundwater flow in a wilting point soil? No. Because it will be down, much down. If the water is there, then the soils will pull the water up. The plants can pull the water up. And this phase won't be there. So the phase actually exists for groundwater. The best phase is the saturation phase, where water comes down, soils are full of water. It can take water for the plants, and the remaining water goes down for percolation. Is this the same scenario throughout the depth of the soil profile from the top of the surface? No, it's not. Why? Because there are changes in groundwater storage with depth in the Earth's crust. Let's take the Earth's crust. This is the top of the Earth, and you have different water bodies and rainfall occurring. Okay, let's leave the terms out. For now, let's discuss 3 to 4 depths in the soil profile. And the profile goes up to the bedrock. The bedrock is the rock which is not weathered yet into soil. So those who are civil engineers and earth scientists, they know the process of soil formation, and there are some NPTEL courses for it. How soil is formed? It's because the rock, which you see on the top, on the bottom, weathers, okay, disintegrates, is acted by natural forces to form smaller particles, and it becomes soil. You could see here, this is black in color, then brown, brown, brown. So I'm not going to get into the soil formation process, but I'm going to show you that the bottom part is still consolidated. The rock is a rock, whereas the top part is, it is unconsolidated. It is converted into soil. So now let's walk through as a water that falls on the rainfall on the ground. So rainfall is occurring, or water stored here is there. It is available for recharge. So water is recharging. Once it hits the top part, there is a lot of pore space. The pore space, which we saw in the previous slide, is available because plants have created that space. The soil itself is in a very good aerated mode, and less compaction. More space is available for infiltration of water. So most water is at the surface in sedimentary rocks buried at shallow depths. Shallow. So there's 4 depths: shallow, shallow, another shallow, middle range, and deep. Okay, let's call it that way. So there is fresh water which entered and it's stored. Now, if it is saturated, water will still move down. So now we go to the second layer around here. What do you see? It is also similar to the previous layer, but the pore space is less because some more solid is there, more solid particles are there. So water gets stored in the second phase. Then you move further down. If you go further down, the rocks are not as well developed into soil in this stage. It is not much weathered. So you still have the structure of the rock. You can see here the structure, the platy structure, etc. And that allows more compaction and also arrangement of your rock material, that the pore space is limited. Low porosity rocks with high salt content. Leave the salt quality out, but right now we'll just focus on, is there space for groundwater? Not much. Okay. Porosity and water content generally decrease with increased depth and greater structural deformation. So if you go down further, you have more solid material. So if you look at solid materials less, increasing, and much more. So the solid material is there more, which means your space for water and air is less. And that is where it becomes extremely low porosity, extremely low water availability for groundwater. With increasing depth in Earth's crust, porosity decreases. The space for water decreases. So groundwater abundance decreases. And groundwater becomes more saline, which we'll be looking at up in the water quality slides. Coming back to your understanding of this to apply in field. If you're a farmer, you put a well here. Are you okay to get the water? Yes, because you have good water supply in the pores. You can easily drill also down because the solid material is less, so drilling cost would be less. But when you go further deep, what happens? The drilling itself is a very complex process. You'll have to beat through all these solid materials. And even if you do, the probability of hitting a water pocket to get the water is very less, or a porosity high region in the deep aquifer is less. Here the probability is much high, and the pores are interconnected, so it will flow. Even if you misplace your well, still water can flow. But here it's not like that. You have to be, for example, if it's a fracture, like we saw here, if you do not hit the correct part in the fracture, you miss the well. If you put it here, there's no water. If you put it here, all these fractures will contribute. So that is what is important to understand. When you understand, as with depth increase, the porosity decreases. With porosity decrease, the groundwater storage also decreases. So there's no point in just going on deepening your well. If you go to rural areas or urban areas where they have wells, just ask them, have you deepened your well in the past 10 years? They will say yes, because the ground table has gone down, the level of water under the ground has come down. So I have to put more labor into deepening the well. Most probably they would put the rig back in and then drill deep, or they'll just abandon the well, go to another location and drill freshly. Because same cost, just you have to do the piping, etc. So understand the theory that for groundwater, you do need to have a space for the water to infiltrate and store. And once the space is connected, it can flow. Let's go to groundwater and the hydrological cycle. Now I'm going to focus only on the groundwater hydrological cycle. So of the overall cycle, we can focus on just the hydrology part for groundwater. Okay. Let's differentiate that. So you have precipitation, which is overall hydrological process, and an important component in the groundwater hydrology. Then you have channel, overland flow, which is fed by the precipitation. So when precipitation happens, water can run into the rivers and some water is lost. Fine. So now these channels and the land which gets the precipitation can provide a pathway for water to infiltrate. So infiltration happens, you see here, the first stage where water moves into the soil profile. And the soil profile is categorized as the top part is unsaturated, which means there is less soil moisture, or the space between the soil particles still has space for water, because normally it is with air and water. And if it is fully with water, it's saturated. So as we move down, that imaginary line comes up, which is your water table. You can see here, it's called the water table. And underneath the imaginary line, all the pore spaces is full of water. It is called a saturated zone. So infiltration occurs far and good. Now you hit the water table, okay? And you start to flow because you have created a gradient. Why does water flow? Any water. Water flows because it wants to be in the most lowest potential. So if you have two wells or two water levels, and one is low, this water would flow to this part because water wants to flow from high potential to low potential. If it is isolated, like for example in a cup, it's okay. But if they're connected through the pores, the law of nature says it has to flow from high potential to low potential. Same like your temperature. Temperature goes from high to low. It has to equate, it has to balance. And then, for example, it is like these two, the high potential, low potential. Water will flow until and otherwise it is the same. Okay. And then there was no flow, or it will always flow because it wants to get to the oceans, which is the least potential, zero. So that is the mean level, zero. And until it reaches zero, it will flow. How fast it flows is dependent on the fluid properties and your solid properties, which we will see in the following slide. So based on this, we can have a systems approach, representation of groundwater hydrology, the hydrological situation. You have precipitation. Part of the precipitation goes as interception, which means the plants and trees which are there can actually cut through the rainfall occurrence and catch the rainfall. For example, you have broadleaf trees, banana leaves, etc. So when rainfall happens, you see the trees are wet, which means some volume is captured by these leaves. That is called interception. What happens to the interception? It becomes interception storage and evapotranspirates. Mostly it is evaporation because sunlight is falling, it evaporates. What happens to the remaining? It goes through the trees. That is called through fall, through the trees, through the plants, until it hits the land surface, which is here. Once it hits the land surface, what happens? Part of the water goes as overland flow, which means surface runoff. The remaining water goes down further deep as groundwater infiltration or soil moisture infiltration. So water infiltrates into the soil, goes to the unsaturated soil moisture storage, which is your soil with less amount of water, more air. So water will go in and replace the air because water is heavier than air. It can replace it. And then some part of the water is taken up by the plants for transpiration. Some of the water, the groundwater in the soil moisture, can go as interflow and into channels, which is rivers, and then go as runoff. So once all of this goes into the rivers, it goes as runoff because rivers then join your ocean. What happens to the water after you're unsaturated? It goes to the saturated zone, which is called the groundwater recharge. So here it is soil moisture recharge, infiltration, and here it is percolation into the groundwater recharge. So what happens here? Groundwater recharge is happening. It goes into the saturated groundwater storage. So there's already a component in your soil profile which has water fully, which means all the pore space is full of water, and that is called the saturated zone. Into that it will go. So what happens when the saturated already has water? So where will the water go? All it does is it raises its level. So here also soil is there. Here soil is there, but this soil has water. So what it goes, the soil would just, the water table will just go up to the soil where it is not fully water. And now the incoming water can store. It can store, and part of it can be taken by plants and trees and released back into the atmosphere as evapotranspiration. Whereas the remaining can still go as base flow. Again, why does it go as base flow? Because water flows from high potential to low potential. And if your river is at zero or your sea is at zero location, then water will eventually flow down. So on the whole, groundwater cannot just stay there. It has to move. How fast it moves depends on the depth in which you have the water. But eventually it will move into the base flow, and then base flow goes into rivers, which is your rivers, stream, storage, etc. And then that contributes into runoff. Okay, so the runoff happens, which is your stream discharge, river discharge, and eventually all of this, all the rivers, all the streams would go into your oceans because that is the elevation. Why does rivers flow from a high potential to low potential? Because water wants to go from high potential to low potential. You have a waterfall. You don't see water going up, right? Waterfall. So water comes around the mountains, and from there it falls down, goes through the rivers, and then goes meets the ocean. For calculation purposes, oceans are at zero level, and that is where we say that is the zero height. And from there we say what are the elevations. With this systems approach, I would like to conclude today's lecture. I will see you on other side of lecture 5. Thank you.